I'll be talking about the, real-time machine learning in streaming data pipeline. So basically, I will talk about the machine learning, the streaming, and the real-time. But I will be talking about the implementation of machine learning in real-time in streaming pipelines, what type of models we can have, how to implement it. This is relatively general talk in terms of how we do it, what are the pros and cons, but not to be too much of Martin Fowlery about it. I actually have some codes and some demos, so I won't be only philosophical about it. And yeah, let's start. And once more, thanks for having me here. So I'm very happy to talk to you. In terms of introduction, I am lead data scientist at SeekDelta. It's our data science software house, we call it. Basically, we solve companies' problems with data science in general. I used to call myself actually an engineer that knows some equations because, as colleague said, I've graduated, I have a PhD in engineering maths, but after that they start calling it data science, so I actually now call myself data scientist, not engineer that knows some equations. I'm also a trainer at SAGES, or SAGES. We teach IT things. I'm responsible for the analytics and data science things, but in general we do IT training. I'm also a lecturer at Warsaw University of Technology when I teach, analytics as well, data science. Yeah, in short, I can code, I can do maths. If you want to contact me, these are the contacts. If you want to talk to me, you can talk afterwards. I hope I'll have some time for questions, but I'm not sure because I don't have a clock. So please wave at me if my time's running out. The rise of big data. I don't know if you noticed, but we have a rise of big data for a few years now. Actually, it started around 2002, 3, 4, it depends how you count. In most of the companies, it started about 2012 when they started to notice that there are some big data problems, but actually, this year it has been cancelled. There is no more big data, there is data. Basically, a lot of companies have big data problems, which are called now the data problems. So big data is no longer a thing by itself. It's basically everyday problem, so we have to deal with it. And also, it became a little bit of cliche nowadays, so I won't be using big data word too much in this talk, I hope. The rise of streaming, actually, nowadays, quite a lot of stuff we want to do in analytics, we want to do in streaming, so in kind of real time. We used to do a lot of stuff computationally using batch computation, so we have some data, the data is lying there, is basically more or less static. We do some analytics and then we have an answer, but the problem is it takes a long time. I mean, you can get like report in 2 weeks about, I don't know, your credit card being stolen, so some problems require streaming, and I wanted to be a little bit quantitative about why, to show the rise of streaming nowadays, and so I say, so we have about 7 out of 16 talks that I can actually track in this conference that talk about some kind of streaming. This is actually logo, if you don't know it, this is Spark Summit. I'm a Spark guy, by the way, so I'll be showing quite a lot of Spark today. Spark Summit have a separate track just about streaming, so that's a big thing. And if you haven't heard about Fling, you should. And they have a whole conference about streaming because it's a streaming technology. So if this won't persuade you, I don't know what will. The rise of machine learning and AI. That's another topic I want to talk about a little bit. So nowadays, everyone wants to do what is called machine learning, and this year even AI. By the way, AI, as the trained machine learning models, are not AI. AI is AI, basically. So that's some companies do call trained machine learning models AI. So, for instance, this is the offering of Amazon that we have, being, again, quantitative about it. These are all the services that Amazon shows it's related with. Oh, sorry, I have the... so these one are actually trained models, but there are some utilities for training models as well. Or maybe I can use it, actually. Google Cloud Platform has also quite a lot of services. Some of our trained models, some of their are training utilities we can use. And Azure has a lot of things we can use actually, so I think they're a little bit ahead in terms of how many they have. So that, well, this should prove to you that actually machine learning is on the rise. So apart from the companies doing machine learning and data science, there's a lot of stuff going on in business offering either utilities to train machine learning models or train machine learning models as a service. So yes, where we are in this, in all of this as data engineers, as data scientists, as developers, actually, if you look at Gartner's prediction by 2020, predictive and prescriptive analytics will attract about 40% of enterprise new investments. This is what they predict, and it's actually what I checked, because this prediction is not super new, but actually it goes along this kind of trend. So actually, quite a lot of companies invest in analytics. Sorry, I have to drink a little bit because, as usual, before something important, I got a little bit cold. Anyway, another reminder, before we start actually doing machine learning here, let's remind ourselves what is data science process. And that actually has been borrowed from this one has been borrowed from data mining process, but the data mining process has been borrowed from scientific process. So what we do if we want to do data science. So first of all, so maybe start from here. Actually, explore and model, this is what most data scientists are excited about. And this is the stuff you get at the conferences, this is the stuff you get at blogs and blog posts, and all the excitement are here, but actually, these bits are super important if you actually do data science, because data science doesn't really make sense if it doesn't have a value with it. So you have to actually create value for business. Well, that is not only my opinion, by the way. You have to create the value for business. So first of all, you actually have to ask business what they want. So that's the first thing, and that's most important thing. You have to remember that data science and also data engineering is not archetypical development process. You don't sit in a basement and code all day, every day. There actually is a business process. You have to talk to the business, you have to ask the business what are the problem, and you have to solve the problem in meaningful ways. And also you have to communicate the solution, because you have to remember all the stuff we do is really imprecise to some extent. I mean, we can measure the extent of imprecision, but it is imprecise in general. Then we usually have to get data, and as Professor said, this is my favorite thing about big data in general, it's a mess. Big data is like basically, if you work in it for some time, it's a lot of messy data. You have to deal with it, and it's coming from different sources. It's of different quality. You have to enhance it. You have to put it together, and this is what big data or data nowadays is about. So data analytics is about, you have to get the data. You have to get the data clean. If you haven't heard about let's say, sentence garbage in, garbage out is very important in data science and model building and prediction. If you feed any model, because model building in general, I don't know, how many of you, maybe let's have a rise of hands, how many of you actually did some model building? It doesn't really matter what the model is, you can call it a model, it doesn't have to be super new machine learning, it can be some other predictive model, maybe line trend, something like that. How many of you, can you just please raise hands, how many of you? Okay, so we have about half people did some machine learning. So if you know, nowadays actually we have quite a lot of utilities, so building a model is actually not very complicated. But if you feed it with some garbage data, you will get a garbage prediction or garbage classification, basically. So you have to be very careful about it. You have to explore, communicate, and you check. And actually, I didn't manage to put the arrows in between, but you can go practically from any process back to any other process, because you usually go in circles all the time. In terms of model, how usually machine learning works in general, and that's important because I'll be talking about how this can be different in streaming. We did usually 3 things, and I was talking to my student, I was working in natural language processing. At some point we were doing named entity recognition models. That's basically a model that says, can say if, I don't know, Jan Sobieski in this sentence is a king or a street, for instance. Yes, that's the model basically can find this entity in the sentence. And basically what we did, the first day of the project, we actually had a model already, but it wasn't very good. But the model building itself it's not very complicated. Actually, we spent most of a year basically cleaning data, building the model, and validating it. So that's the process you actually get. And as you can see in streaming, it gets a little bit special at some point. Okay. Streaming is not easy. Again, rise of hands. How many of you did what you can call streaming? And I'm not saying piping in Linux. I'm not saying cut something grep. I'm saying streaming like Spark streaming, Flink, Storm, things like that in big data. Can you? Oh, Akka as well. Akka counts, by the way. So a few were. Okay, so for those of you who didn't do streaming, streaming actually is not easy. Why streaming is not easy? Because stream is infinite by definition. So how to work with something that is infinite by definition? Well, it's tricky. Also, streams have to work, theoretically at least, have to work all the time. So they have to work for, not like batch jobs for minutes, hours, or days. They have to work for weeks and months. I actually have, on the project I am, and it's really kind of proof of concept project at the moment with Hypermedia, we have easily codes that go in for 3 to 4 months at the moment, and they work quite fine. So that you have to remember about that you're writing a code that will be constantly working for a long period of time. So from the engineering perspective, it's not easy, and from analytics perspective, it's not easy because this is actually taken from structure streaming, the manual for how structure streaming works. As I said, I'll be using Spark because this is kind of closer to bone for me, but in general, the things I say can be in general used in other streaming systems. So what happens here, as you see, actually in this mode, the data basically grow every time, and you actually calculate some aggregate over this data. So that's one of the things you can do. You don't store the whole data, you just store the aggregate, or at least one of the part that you do is storing the aggregate, and you can do something with this aggregate. I'll show you in a second. Also, one introduction to not to be overly general about things. I'll introduce hello world of online stream modeling, or in general the example that is often used in stream data processing. As an example, it's Kmeans clusters. And a reminder for you that haven't heard about Kmeans, basically, I will show a picture and demo at the second, so you will understand slightly more. I'll be using this approach. This is actually a Google paper from 2010. It's called Minibatch Kmeans, and this is used and implemented in Spark, but it's actually, I think, most used K-means model at the moment. And actually, I won't go in details here. Basically, you have to, I'll show it on the demo so you will see what happens. I don't want to read through it. You just basically have to find the centers and then update where the new centers will be. The important bit here is this eta. That's not n, that's eta, Greek letter eta. This eta can be actually 3 things. In here, the eta is proportional to 1 over n, so the number of points you have here. And that's good for if you do a kind of static model with the centers that don't move anywhere. But actually, as I'll show in a second, the centers can go kind of sideways and move, and you may want to update. So there are 2 approaches. Either you can, instead of having n, which is proportional to 1 over n, you can make it constant, or you can be proportional to alpha, which is kind of it's called a decay factor often, and basically it's some number that will say how much you have to remember the data and how much you have to forget about it. So in cases, or speaking more plainly, how the new points matter, how much the new points matter compared to the old points. Okay, how it works. Well, this is a picture of the demo, but actually this is just to show you that I'll have a demo, and let's hope everything works well, because I'll be running some code. By the way, if you want, so I won't be going too much into the code, apart from explaining what it does, because I don't have time for it. But good news, actually it's on my GitHub repo. At the end you will have a link to it, so you can download the code and try it yourself. I hope it works. I mean, it works for me. So, yeah, as usual. So for the first demo, I use. Actually, by the way, as the colleague mentioned, but I'm kind of in between JVM and Python. I actually spend more or less the same time in JVM, mostly Scala nowadays because, well, I like it more, and Python because Python is a very, very good tool in terms of big data and analytics and machine learning, and definitely go-to tool if you talk about deep learning nowadays. So that's a little bit of an introduction. And how it works, I will use bokeh visualization, which is if you heard about, can you see that? Is it visible from the back? Sorry. Well, I can see that. I don't hear any complaints. Is it okay? Great. That's basically a form of dashboard. So what I will show here is this is actually a running simulation. The cross in the middle is the actual centers of the cluster. They're real centers, and the points are generated around those centers are just random points around those centers in some radius. And as you can see, this cross, so the X here, I will call it an X. X here kind of dances around because it gets updated with this alpha. And this is the alpha measure from the formula you've seen before, and I can go up with it and down, and you don't see too much happening apart from if I go down, it slightly slows down. But actually, so that's kind of the archetypical case you get in the batch machine learning quite often. But there's also a special case when something happens to the centers, and they will just go in circles nowadays. At the moment, they start to drift. So because we have, for example, streaming model, and our underlying process, whatever it is, changes. So what we can do is actually update on it. So you can see that this model, as I said, this is not a streaming per se. I will show it in the streaming in a second. This is only simulation done in bokeh and Python. As you can see, this model adapts to it because basically the alpha here is quite low. If the alpha is quite low, it actually converges to the cluster very quickly. I can't really speed it up to move quicker, but if you go up with it, you will see that with time it gets lazy, and actually at some point the points will get stuck. So this is the point if you want to have some static clusters in general, and there will at some point they will just start to they will split evenly the space here and just classify the points as they have, static clusters here. And that's also a case you may want to consider. I just wanted to show you that this alpha is important, especially if you have a drift. If you don't have a drift, it's not that important, but just bear with me in terms of in a second to see the why it will be important in the real streaming job. Okay, so I can close that just to be on the safe side. I will close the demo, and again, as I said, don't worry. You don't have to, take it down on your laptop. You can download this code later. It's actually also Apache license, so you can do whatever with it. So don't worry. I mean, as long as you can do really whatever with it because it's Apache license. Okay, let's go back. I will have later some demo with. Okay, how much time I have? Oh, okay, I still have some time. Okay. Training model so we go back now to the models. I just want to have a little bit of interruption to show you how K-means work. I'll use it more extensively ever so slightly later. Now I showed 3 situations, really 3.5 to some extent, how you can productize a machine learning model in a streaming pipeline. I will use Spark as an example, but you can have really any streaming system here because most of the systems, at least I know, will work more or less the same way. And train models in the streaming pipeline, what's good about them? So you have generally the same process of creating the model, and you do it on the side. You train the model. If you're happy with it, you say, okay, let's use it in our, well, whatever production is, but on our production. Sorry, I have to drink it again. Let's use it in our production. So what you have to do is take your, this is the model training. You have a model in a language. Here it's in Java or in JVM because we're in Spark. And Spark, as a reminder, is predominantly in JVM, despite the fact it has APIs in Python and R. The internals are inside of JVM. It's mostly in Scala and Java. So the best way is to have a model implemented in JVM-friendly language, and what you do, you create an object in a driver. So basically, you create this model in a driver, and since this model is ready and hopefully also thread safe, you can just distribute it to your executors that do the actual work. I mean, on Spark, they call executors. In your favorite streaming system, they can be called otherwise, but this is how it works. The black arrows here indicate the distribution of the model. And this is what you do. This is what a lot of people do in practice. Often in Spark, you would use libraries like Spark MLlib, which is kind of ready-made library that models you can train and distribute relatively easily. Pros and cons of this approach. What is good about it? So you can develop the models as usual, and that's quite important because you know how good is the model. You can validate it. You can go back and forth with it, and when you're happy with it, you can deploy it. Your models are part of processing pipeline, so basically you can't really go. I mean, to the let's say, as far as technology goes, you can't go any faster. I mean, you can implement the model in some faster language than, for example, Java. But other than that, is probably the fastest way in general you can go. Models can be distributed efficiently. It's usually streaming systems and batch systems as well, like Spark, have some efficient way of distributing the model, serializing them. You can use either the built-in serializers, or you can use things like broadcast variables. To my knowledge, I used Flink a little bit. Flink has similar mechanism, though it's the underlying mechanism is slightly different, but it works the same. And the model scales with the system. What does it mean? Because as you probably know, a lot of big data systems have this functional paradigm that basically you don't have a state. So basically the model don't have an internal state. Well, it shouldn't have at least an internal state. You just train it and you feed it with data, and it gives you an answer, and you can split it into many pieces, and then all of the pieces will give you a hopefully at least correct answer. So this problem can be quite efficiently scaled with a system. You don't really have, from the model perspective, apart from the model speed itself, from how you build the model, you don't have any bottlenecks here. What are the cons of this approach? So it's harder to update because you have some serialized objects, so you have to do some clever way of updating it. Again, you have some mechanism in things like Spark, and nowadays in Spark 2.0 you can quite easily manage, for example, broadcast variables, and you can unpersist them and just put another object in there. It's one of the ways of doing that, but it is slightly harder. Programming language should play well together. I mean, despite, for example, the fact that Spark supports many programming language, actually, if you want to go faster, you should go Java Scala, because it's the internal language. If you go Python, it will spin an additional Python on the side, and you have to pipe the data back and forth between JVM and Python, and that's actually considered in Spark and a little bit of anti-pattern. So you shouldn't do it quite often. So you're slightly constrained with the programming language you use. Serialization can be problematic. A little bit of shameless plug here. I actually, on our sigdelta.com blog, I recently posted a post about what happens if you want to serialize unserializable or not serializable object in Spark, and how to go around it. So if you want to look into it, it's not very complicated. It's just a solution to this problem, but it can be problematic. You often have to wrap it around in some additional object to serialize it, because the model you're using may not be serializable. Models should be thread safe, so that I said, because otherwise you will get into trouble. And model are often passed down to engineers for productization. I think that's the biggest problem. I mean, because you have this silo effect here that, the data scientists create a model and then it passes down to the engineer and it has like variables like M1, M2, and M3, and then engineer has to figure out what they do. And it's not hard often. So you have to remember that data scientists, or well, scientists in general, are usually not super good coders. So you have to remember that here you have to pass the model. And if you're lucky, you may just pass some properties, but often you have to pass actually the whole thing to re-implement in some other language like Java. Other approach, containers et al, I call it. So basically wrapping our model inside of a container. It's actually very similar to the previous one. It's like a 1.5, this half solution I said about, sorry. So your model building process is exactly the same. You can do the similar model building approach. And you can use your favorite language. I put Python here because I like Python and I use Python. It can be R, it can be pretty much anything. If you like Haskell, it can be Haskell. Doesn't really matter because you will put it in a container and you will create a web service out of it or some other approach along this line, but it basically will just have some API interface to it that will be separate from the implementing it from the processing pipeline itself. And what happens here is you have to wrap it out in, well, I've put it Docker here, but you can put it in anything. My colleague here from IBM will talk about implementing this in IBM ecosystem, and with a similar approach, you can listen about it. There is also quite a lot of information online about how to do it. So it is, I would say actually this approach is one of the most popular approaches nowadays for running models on production because it's well, I would say most efficient. Yeah, I think that's a good word. You put it in some sort of a web service or a service, and basically what happens is your data pipeline, and now the orange, sorry, it looks orangey, but it's actually yellow. So the data here, the data goes to executor, it's being passed to the web service, and the green line, which is the answer or result, is being passed down to executor. So basically the executors do some external call and get the data, get the answer from the machine learning model, whatever it is. You'll get it, and yeah, so that's how it works. The pros of and cons of this approach. So the pros is you can develop models as usual again. It can be done almost with any tool of choice. That's a very good thing for a data science team because they can use anything. They can use R, they can use Python. When they will be happy with the model, they just have to package it and deploy. Deployment can be done by models creator. Usually it's not done directly by them, but the engineers usually create some sort of ecosystem for them to wrap the models up. But basically, the data science team is responsible for model productization. Also, the side effect is it's easier to incorporate into continuous integration, continuous deployment pipelines because it's kind of a separate thing. You can send out somewhere to be tested, basically, because it just have interfaces. The interfaces can be easily tested. The data responses from the interfaces as well can be tested quite well. So that's another good thing about it. You scale it by cloning, so usually. So you basically just have like one instance at the very beginning, and you just create as many web services as you need, or clone as many Docker images as you need, and that's how you scale. I mean, given that you have a proper machine, also operations ecosystem underlying it. Other good thing is multiple version of a model can be run at the same time. So this really is important when you, at some point, for some reason, change the API. Basically, if you change the API, if we go back to the first approach, you have to rewrite your whole pipeline. Here, you can just send the model out, and then when engineers are happy to rewrite their pipelines, they will do it and that's it. And it's very easy to update again because you just have a Dockerized models. You can send them out. You'll get the responses. I actually forgot about one point here that it can be also used by any other services. So basically anything that is API capable, and it's usually either REST or some sort of RPC interfaces, then you can call it. This can be your web services. It can be your data pipeline. It can be anything that can communicate over a network. Well, what are the cons of this approach? So extra work for modeling team. I mean, modeling team has to get to know some sort of rigor of productization of the model. There may be some new technologies like Docker or some other maybe cloud system involved. Well, containers also are web services that have to be done properly. I mean, you have to extra bit of code basically that can have bugs in it. There is an extra service to maintain. May become a bottleneck if it's slow for some reason, because it's, for example, I'm not saying about the model. The additional bottleneck can be related with the implementation because you use, usual thing I often see in kind of web service world is you happily use some sort of asynchronous API and you block it. So that's usual what happens. It's prone to network issues. I mean, because it communicates over network. If the network is down for some reason, and there are separate networks, and that also often happens because you have like containers cluster on one side, computational cluster on the second side. If the network between them even goes down, then your computation goes down as well. I would say I don't think that's a very rigorous, but I would say it does require DevOps culture. You have to have a proper DevOps pipeline to develop it. And yes, it's pros and cons at the same time. I would say looking at the what state of maturity on DevOps in general, not maybe calling names, then yeah, I think I would put it in cons at the moment. So, and basically you have to remember this is pretty much a microservice. So all the pros and cons of microservices you will get here, basically. So, and just a reminder, if you haven't heard this word, microservice hell, this is what you're looking for. Well, you're not looking for, I'm looking to avoid, maybe, okay? And I'll be talking a little bit more extensively. Sorry, I'll look how much time I still have. Oh, I have plenty of time. Online machine learning, I want to spend a little bit more time on it. This is a special case of machine learning that you create the models and the models update themselves. So it can be any algorithm. Online algorithms are different algorithms. They don't have to be a machine learning algorithm, but I'll be talking about machine learning algorithms mostly. And there are different things about it. So if you remember our streaming pipeline here, we have this data coming in. It grows. You have to do something with the data. And now, as you can see, our data update or model creation pipeline changes a little bit because from being kind of going in circles, it actually got flat. So we just do three things. We clean the data up, we update the model, we do some sort of evaluation at the end to prepare the results and push out the results like here. And this is the axis of time. So this is the next, let's say in Spark world, it will be some micro batches usually for example, if you're in Flink, you usually somehow batch the data as well, at least for this process. It may happen, not necessarily maybe, but often you do. So if your time progresses, your model is getting, well, different and different. I don't want to say better and better. It may become better and better, but not necessarily. That's the problem of this approach. You get the result out, so your data science process goes slightly out the window, and that's a little bit of a problem. Okay, so maybe let's do a quick go back to IDE bit. So what will happen here is I will show how this model works, and I will slightly explain a little bit of the code. Here, actually, I have to. If you go on my repo and look into it, I have two implementations. I'm not sure how many of you are familiar with Spark, but in general, maybe did some at least examples in Spark and know the terms. Okay, so again, half. So Spark has this, this big change with 2.0 version that it introduced quite a lot of new things, and actually the first-class citizen became the SQL interface using their data frames and also SQL queries became a first-class citizen in maybe, yes, this one, became a first citizen here. So actually, we can work with data frames, so kind of a tables of data and structured streaming, because this is this extension called in the streaming mode, will take care of the data for us and will allow us to do some queries on top of it. Or you can use models as well, but if you will use it using the data frame or SQL, mostly in streaming data frame interface. By the way, if you don't recognize this, this is Scala. So yeah, you have to deal with it at the moment if you don't like it. It's slightly easier to update, to do proper streaming in Scala. Unfortunately, Python interfaces are not that good at the moment. So what happens here? You actually do pretty much the same thing. I have a Scala socket server that creates some data for me and put it on a plain old text socket. Sorry, where's the job here? Here I basically read this from a localhost socket and create a data set actually here out of it. And I use a model, which I actually created the Kmeans model. I create this model and use this model inside this pipeline using the data frames. And as you can see here, there is this evil train thing that basically every time for every micro batch, the model will be retrained again. And that's called evil train because of one thing. If you, basically there are two streaming APIs. There is what is called Spark Streaming, which is RDD based, this original interface, and there is interface in Spark called Spark Structure Streaming. And in Spark Streaming, the original one, there was this very nice function called for each RDD that it was easy to get back data to the driver and update your model quite easily. Whereas Spark Structure Streaming doesn't have it as of yet. I used Holden-Skarau approach using evil, how it's called, sorry. I actually ported it because it doesn't work with the newer version. Evil Streaming Query Manager. It's called Evil, and this Evil Train is called Evil Train because it uses the internal Spark API, and it's a little bit of a hack. I mean, it's not tremendous hack, but you have to tap into the internal APIs. I just modified it and also modified the model because it didn't have a decay factor in it. Again, you can download it for GitHub if you're interested, but basically that's a adaptive K-means model, and it will label the points and again write them out on the socket again, because I have to, for your entertainment, I have another Bokeh server. This time it's a server that just takes a data from a socket in Python this time and plots it out in a similar way as you've seen on the previous demo. So again, I don't want to go down into the codes. If you haven't heard about Bokeh, you just go for it. It's very, very nice. If you heard about structure streaming, again, read about it. And what I wanted to say again, there is a version with dstream job, which is the older streaming job. If you can run it, that's ever so slightly simpler. I mean, there is less coding a little bit, mostly because the model is implemented inside Spark MLlib, and you can just use it. You don't have to write it yourself, as I did. Yeah, you have to spend slightly more time, less time on sending the data out. But yeah, as I said, yeah, I don't have, unfortunately, time to go into details here. I just have to start three things. So I'll starting my streaming job. Oh, sorry, not this one. I have to start the socket server first. Maybe it will start, yeah, it is easier code, so it started earlier, but this will die because I don't have a K-means streaming. or won't. Sorry, just a second. I may or may not need to restart some. Let's see how it goes. Yeah, this is the live code for you. Does it work or no? It works. So now you actually have a this streaming model streaming server is actually already implemented with a drift. And you have a model that basically I think alpha is 0.3 in this case. So it basically follows your centers. As you can see, it's ever so slightly slower, because I have quite a lot of stuff running, which is pulling data in and out of sockets. So it actually uses my computer quite badly, and well, in general, streaming is tough. So yeah, it takes slightly more time, but as you can see, it pretty much works. Again, if you want to see those codes, you can just go to my repo. It will be at the very last slide of this presentation. I will post this presentation somewhere as well, maybe on the repo, maybe on the slide share. So don't worry too much about it. But as you can see, it works and it follows the cluster. But as you can see, it also have a little bit of error in that sense that it follows actually the new points kind of more rapidly. That's why our cluster centers are kind of a little bit in the front. If I lower the alpha, it will be slightly slower with the adaptiveness, and it'll be slightly more in the center here. So. But yeah, the classification is basically maybe not always looks good, but it actually in the long run is good. So you have a good thing here. So you have a model that basically you put in your pipeline, it updates itself, it follows some trends you have, because with the streaming data the trends can change. So this model will follow, and it's, well, in general you can say it's a good thing, and it actually classifies not too bad looking at this plots here. Okay, maybe I'll just stop this job and prove to you that these are the points just printed out. Let's check if the dstream job still works. Yeah, dstream jobs is ever so slightly quicker, but it's mostly related with the implementation of it. But I think how it draws the data broke a little bit. Yep. Yeah, but in general, I would have to probably restart the Bokeh server because, oh no, sorry, the exit got updated as well. So that works as well. So yeah, that's the other approach. I just proved to you that using the RDD tool and the existing K-means model also works. So we have a good thing here. We have a model. It works relatively well. It follows the data. It follows the drift. Yeah, job's done, you can say. Okay. Let's kill it because I'll drain my battery in minutes otherwise. Okay, I think I have to speed up a little bit, go back. Okay, so we have this model here. What models you can use? Actually, quite a lot of models. A lot of machine learning models, as of now, are capable of being online models. You can retrain them. They're actually quite good with it. Obviously, K-means, because I just showed that. But most of the general linear models, like linear regressions and regressions in general, work quite well with it. Support vector machines, adaptive boosting neural networks, including deep learning, and, well, anything that can be learned iteratively. I just actually listed the machine learning models that are usually somewhere pre-implemented to work as online learning models. In Spark streaming RDD, you have definitely linear regression, K-means, and something else, I forgot what, already implemented in MLlib, so you can just use. There is a little bit of a problem with the online model. Well, one of the problems you can encounter. Your models live in a driver. They live in basically a place that you have one model. Because you have to remember, you have to have some sort of a global state to have this model. Why? Because effectively what happens is you pull the data in, you train the model on this data, and you have the same model, the whole model you have to serialize somehow to executors and use this model for training. And if you think about it a little bit, or you use Spark, or in general you code quite a little bit. If you have a state, and if you have a single object you have to update, that's a bottleneck. Yes, that will slow you down because you have one place you have to get all the data. I mean, you can optimize the training a little bit. You don't have to, do all the calculations. And actually, if you look into this code, a lot of calculations is still done on the executors. I just pull the aggregates to update the model, so it's not completely pulling all the data in the driver. So it shouldn't blow up your computations. You have I'm going on and off. You have a little bit of a bottleneck because you have to have a state, one state, so one object that gets updated and get sent out, because the classification pretty much works as it worked before. Pros and cons of this approach. Obviously adaptive, you've seen that. Yeah, if our cluster centers change, it adapts with it. It's a part of a integral part of a streaming pipeline. It updates automatically, again, we've seen that. Some models can be quite quick. I mean, some of the models like Kmeans actually don't require very much computation. You just basically pull the center aggregates really and use averaging basically to update the centers. That's really it. It's really two vector operations really you do. So not very much, but you have to still remember you have to go back with the results and update them. And you get pretty much instant results, but by instant, I mean, because it's a part of streaming pipeline, you get the results of your model quite quickly out. And this is important when a lot of your processes have some underlying changes, like drift, or your level can change or something like that. You know very quickly about it. Usually, if you have this traditional machine learning model creation, you have to basically retrain your model to adapt to the new changed environment it works in. Cons. Very little models are actually, very few, sorry, I should say, very few models are actually implemented out of the box. So you have to actually code quite a lot, and often you have to code in languages that are not necessarily data science friendly. They much rely on the internals of the streaming system. So as you've seen in the previous setting, I had to prepare the data in some quite peculiar way. In the second, I had to hack into Spark and change it a little bit actually to make it work. They may be tricky to implement because you have to remember that you should do it at least semi-optimally, and you have to put it in something that is infinite stream. So it ain't easy. They will, I don't want to say that all of them require a global state, but all of the ones I know require a global state. So you have to go back and recreate the model. In some systems, you can go around it by creating one model per one kind of slice of your data, because, for example, in Flink, you have something like keyed data stream, so you can create one model per one type of key, for example, so you have few models, so it's not as centralized, but then you have to remember you have one model per one key of your stream you have, so that's important. You have to remember that they rely heavily on the internal assumptions. I mean, they will be as good in terms of adaptation as you create them. So, for example, I'll assume that the alpha parameter 0.3 is actually good for this system. It may well be that actually 0.5 is slightly better because, as you've seen, I had a little bit of the cluster center kind of going in front. So maybe it's actually not a good quality. And training also can be a bottleneck. I mean, as I said, this model is very simple, but if you go, for example, to neural network or deep learning, that actually goes quite not very quickly. Let's say still some time. Okay, so, but you've noticed, and you came to this talk, and it has a real time in the title. And actually, a lot of people assume that if you have streaming, you're real time. That's it. And that's actually not necessarily the case. I mean, in some system, you are in some form of real time because your data flows all the time, and your predictions or your data gets there, relatively quickly. So yeah, that's a form of real time. But actually, real-time systems have definitions. As I mentioned, I don't know if I mentioned, I'm a control engineer by trade. So actually, we did real-time systems in, well, 60s. I mean, I've studied in 2000s, but still, real-time systems are being done for ages, forever, pretty much. I mean, in control engineering. What real-time system means is actually real-time system is it's kind of very general definition. It's taken well, it's actually reworded a little bit from Wikipedia, but basically most of the definition says more or less the same thing. Real-time system is a hardware or software system subject to a time constraint. What does it mean? Basically, if you do some computation and it's after the time you need it, then you're in trouble. That's basically what it means. Where it's important, I mean, there are systems that you don't have that much time constraint. For example, if you monitor your servers, I mean, you want to know that your server is down, but waking up your admin in the middle of the night will take at least 30 minutes. So that's not exactly a real-time system, I would say. I mean, because of the the protein interface, between that have to take care of the fault. But you have systems like real-time bidding. I don't know if you heard about real-time bidding. I work currently a little bit in advertisement. Real-time bidding happens if you open a site. Actually, a lot of the adverts you see on the site are being offered in the places on the site, as you see, for example, you can have advert here, and advert here, is actually often offered in real time. And the system just throws and say, oh, someone opened the site and we know this and this about him because he had some cookie ID and some cookie profile, etc., etc. Who wants to buy an advert? And actually those systems, because you want to see your website in kind of, let's say, feasible time. Usually feasible time is between 1 and 3 seconds, depends on the website, and you can trick your system a little bit, but usually for people, I think, for 2-3 seconds, they don't complain. So the order of the latency in real-time systems is about, order of hundreds milliseconds. So basically, you have to place a bid within this kind of 100 millisecond, otherwise you're just not taken into account. So that's a real-time system. You have to react in some finite time. Also, a lot of telecoms have this real-time system. For instance, if you, I don't know, approach the border and the system will say, oh, you're approaching the border. Let's send him an SMS saying, did you buy your roaming offer already, or something like that. This is a lot of these systems actually in place, and they have to work in real time because you can't get this information week after you've been to abroad. That's doesn't really make sense. So yeah, you have to have work within some time constraints, and streaming system may or may not be real time. That's actually what are the real-time timescales? So you have quite a lot of them, really, and these are just examples. So you have things like DSP, digital signal processing, and there is a talk by Intel about FPGAs. I don't know exactly what it's all about, but they are often used for digital signal processing, and their latencies are in things like nanoseconds. So they're very, very quick. You have things also like image processing, and I'm talking here about some image processing like enhancement or stabilization in cameras. It's not like face detection, because this can actually take slightly more time, and that's usually called the real time, real time. And all the stuff we actually, as big data engineers, let's say the word, encounter is what is called near real time. Near real time is when you have a delay involved, and our delay is usually some form of a network involved. So that's actually, if you learn something from this talk, if you'll do real time in the big data system, you will usually do something that is officially called near real time. And as I've here put a latency, this is fast, this is not very fast. I don't want to put time here because it varies. So that I just want to illustrate it. Models versus time. I'm talking about all of that because this is what matters to us in this talk, at least. Also, I mean, I wouldn't bet my hand on this, because actually those models can move up and down depending on implementation and the speed of them. But this is kind of the general thing, that the simple model like K-mean, naive Bayes, or general linear models are relatively quick. I mean, if you use them, they can give you an answer relatively quickly, of course, depending on the implementation, but they're relatively simple, but they can be quickly. Support vector machines, if you use them, it very much dependent on the kernel you use. If you use linear kernel, they are usually not very far from generalized linear models. If you use non-linear kernel, hell gets loose, so usually. So that changes. And all the things like ensembles or convolutional neural networks, or in general deep learning networks, they often are quite slow, and here the slow is maybe not human slow because they can give like an answer within a second, but for our big data pipeline, we can, like for real-time bidding, it can be way too slow. So you have to, so basically, well, the bottom line here is, take this into account when you're building models and offer, if you get a job offer, if you go do like quicker real-time, like this, like fraud detection or the, especially like real-time bidding, you won't go very far with like fanciness of your models, really. You'll go in relatively basic models because you have to be quick. If you have to be slightly slower, you have to detect some faces, people going around, I don't know, an airport. Detecting humans. Let's not go into privacy here because we can spend probably a week talking about privacy in big data. Then you can probably live with 1 of 2 seconds classifications. But you have to still remember that in big data, back of the envelope calculations are quite important in that way that you have to multiply. If you have 1,000,000 rows of data times seconds is 1,000,000 seconds. So go to Google and check how much is 1,000,000 seconds. So, of course, you can parallelize it, but I usually, in the proof of concept system I have about a few millions messages a day. So yeah, you have, you have to remember about it. So. Okay, so that was it. Thank you. If you're interested in the code, go to my GitHub and just download it. If you are interested in what I sometimes write on our blog, I encourage you to go to our sigdelta.com blog, and I write about analytics, but I write about some more technical stuff. So because I'm kind of in between data science and data engineering, sometimes I go a little bit more technical, sometimes I go a little bit less technical, but what you get definitely will be Java, Scala, and Python. That's what you get because this is the stack I use. And thank you very much for having me.